The hidden rings of the Milky Way, what astronomers just found. The Milky Way has just revealed something no one expected, a hidden population of faint, ring-shaped structures, invisible in ordinary light, but glowing softly in radio waves. These aren't distant galaxies or random background noise. They're real features within our own galaxy, and their discovery is rewriting what we know about stellar life and death. It all began with Meerkat, a powerful array of 64 radio antennas in South Africa. While scanning the galactic plane at 1.3 gigahertz, astronomers detected 164 compact ring-like radio sources that had escaped every optical and infrared survey before. Why hadn't we seen them? Because interstellar dust blocks visible in infrared light, hiding these features from traditional telescopes. But radio waves pierce through that veil, revealing a secret layer of structure inside the Milky Way itself. Each ring spans less than an arc-minute across, yet their diversity is stunning. About 40% contain a bright infrared point at the center. Roughly 50% glow in mid or far infrared. Nearly 20% host a central radio source, possibly a dying star or remnant. And some? They exist only in radio, with no known counterpart in any other wavelength. Once cataloged, the team began the detective work of classification. Many of these newfound rings match familiar types of cosmic objects, like the delicate glowing shells of planetary nebulae, which are formed when aging stars like our own sun gently shed their outer layers into space. But a significant number of these discoveries don't neatly fit into any existing category. They stand apart as true oddities, defined by their strange, wavelength-limited nature, making them a puzzle for astronomers to solve. Intriguingly, a few even resemble the colossal odd radio circles, or ORCs, mysterious galaxy-sized rings previously spotted only in the distant universe. The galactic rings are much smaller, but their similar shape is a crucial clue. It suggests that vastly different astrophysical processes, separated by millions of light-years and immense scales, might produce the same fundamental circular geometry. The key breakthrough was Meerkat's unparalleled sensitivity and resolution. Earlier surveys simply weren't powerful enough to catch these faint, compact signals hiding in the galactic plane. With this discovery, astronomers have uncovered a new structural layer of the Milky Way, a previously invisible ecosystem of shells and bubbles that deepens our understanding of how stars evolve and interact with their surroundings. So what are these rings? There are several leading possibilities. 1. Planetary nebulae. These are the final glowing breaths of sun-like stars. As they die, they puff their outer layers into a beautiful, expanding shell that glows faintly in radio waves, like the famous Ring Nebula. 1. Supernova remnants. These are the aftershocks of stellar explosions. The blast creates a powerful circular shock front that plows through interstellar gas, heating it and causing it to glow for millennia, much like the remnant of Tycho's supernova. 1. Massive star wind bubbles. Some of the galaxy's most massive stars, like Wolf-Rayet stars, have incredibly powerful winds. These stellar gales blow huge bubbles in the surrounding gas, sculpting shells that can be seen in radio light. But not every case fits neatly into a known category. Some rings show no corresponding infrared or optical signal at all, making them true radio phantoms. These puzzling cases might not be stellar remnants, but something else entirely. Perhaps the light from a distant galaxy being warped into a ring by the gravity of an intervening object, a phenomenon known as gravitational lensing. Or they could be shock fronts or even magnetic turbulence shaping interstellar gas into these elegant ring-like forms without a central star. Beyond the individual puzzles, the sheer number of these objects is what makes the findings so important. If Meerkat found 160 in a single survey covering just a fraction of the galactic plane, that implies thousands, perhaps even tens of thousands, are scattered throughout the Milky Way. Of course, this is an estimate. Surveys like this have inherent biases. They might miss objects that are too faint, too large, or located in crowded regions of the sky. But even with these uncertainties, the conclusion is clear. These hidden rings fill a crucial gap between bright, well-known remnants and structures previously too faint to detect, suggesting that late-stage stellar activity is far more common than we realized. Beyond stellar evolution, these rings offer a new way to study the interstellar medium, the vast, complex ecosystem of gas and dust that weaves through our galaxy. Imagine one of these expanding shells, a bubble of energy from a dead star, plowing into a cold, dense cloud of molecular gas. The collision creates a shockwave that compresses the gas, kickstarting gravity and triggering the birth of a new generation of stars. Each ring, then, isn't just a relic, it's an active agent of change, a record of energy moving through the Milky Way. This discovery has broad implications for our understanding of the galaxy. First, it forces us to recount stellar remnants. If so many faint shells exist, our census of stellar deaths is incomplete. Our estimates of how often stars die and reshape their surroundings may need a significant upward revision. Second, it deepens our understanding of galactic feedback. These rings are a direct visualization of how dying stars inject turbulence, kinetic energy, and heavy elements forged in their cores back into the galactic gas, fueling the cosmic recycling program that builds the next generation of stars and planets. And third, it marks a new chapter for radio astronomy. Meerkat proved the power of next-generation arrays to uncover the hidden universe. But once the Full Square Kilometer Array, SKA, begins operations, its unprecedented sensitivity will reveal even fainter, smaller, and more distant structures, turning this trickle of discoveries into a flood. So, what comes next in unraveling the mystery of these cosmic rings? Future research will focus on several key areas. First, multi-wavelength studies to pinpoint hidden central sources. Is there a faint, dying star at the heart of a ring, or is it something else entirely? Next, detailed spectral and polarization analysis will help determine the physics at play, whether the emission is thermal, from heated gas, or magnetic, from electrons spiraling in powerful fields. Time series monitoring is also crucial, allowing us to watch these rings expand, brighten, or fade over months and years, revealing the speed and energy of their creation. Ultimately, combining all this data will decode their full physical environments. Next-generation telescopes like the Square Kilometer Array will be instrumental, offering unprecedented sensitivity to find even fainter rings. Over time, astronomers may even develop an entirely new classification system, one that organizes radio shells by origin, planetary nebulae, stellar winds, explosive remnants, or perhaps something completely new. Each ring tells a story. Some mark the quiet, graceful fading of a sun-like star. Others trace violent, still unexplained events. Together they reveal a hidden architecture inside our own galaxy, a glowing, radio-bright record of its dynamic and often turbulent past. The Milky Way's invisible rings are more than a curiosity. They are a profound reminder that even in the familiar spaces we thought we knew best, the universe still holds deep secrets, whispering in frequencies we are only now learning how to hear.